Greetings, ladies and gentlemen. My name is Chiravachradej. Today we'll be discussing a new kind of stress. This one is called shear stress. Similar to the axial stress that can be caused by two different sources. Well, per se, it can be caused by axial force and the bending moment. The shear stress can be caused by two different sources as well. One is by the shear force and the other is by the torsion. We'll discuss on torsion later on. Today we will focus only on the shear stress that is caused by the shear force, which we actually call, well, the one we're looking at is what we call transverse shear. Which then the full name will be transverse shear stress. Okay? The topic for today will be starting as usual. What background do we need to beginning to have a chance to understand what we are talking about or what we are studying here? And then we'll discuss about formulation. There will be two kind of part, two subsection of this formulation. The first part we'll be discussing about what we call longitudinal and transverse shear stress. They are two directional. They both are shear stresses. Now, there will be reason for it. I will explain along the way why do we have to talk about these two shear stresses, which actually in the end summarize into one stress. And once we prove that part, then we use rather than the longitudinal or rather than calculating the transverse shear stress straight away, we actually calculate the longitudinal shear stress, which are equal to the transverse shear stress anyhow. So it cannot relate it. And then we'll prove the expression for the shear stress. Again, transverse, longitudinal, they are the same. Therefore, calculating one, you know the other anyhow. Okay? And then, of course, as usual, we'll see some example on how we calculate the shear stresses. Now, because this one here is about the shear force, therefore, we must be able to calculate the value of shear force anywhere in the structure. Okay? And of course, from time to time, well, most of the time, we must be able to construct a shear force diagram. We also need to understand how the shear stress is distributed, not the shear stress, sorry, how the axial stress caused by the bending moment distributed along the cross-section area. And that because we need to use the stress for the bending moment to calculate the shear stress. Now, if you remember, if this is a cross-section, that one is a cross-section. Axial stress this way, shear stress this way. This is transverse shear stress. It's 90 degrees. Therefore, what we need to do is actually find the longitudinal shear stress. That is the reason for it. Okay? Now, let's see how we relate them. Okay? This is longitudinal shear stress. Now, if we have a beam, any beam, subject to any kind of load, and we look at a small element inside that beam, that dA is the front view area, not cross-section area, the front view area. Okay? Let's look at that. Okay? The transverse shear stress that we actually look at usually coming from y-axis this way. Okay? Notice that this is actually a pair. Well, don't forget this element has the cross-section area on the side. Okay? If we take moment about point A, notice that tau, that shear stress will times the area become force, distance times 0, 0. That one times the side area become force, that distance dx. It is not equilibrium, meaning this element must be rotating, but it's not, because actually what we have is what we call the longitudinal shear stress. In this case, in general sense, in general text, the shear, they use tau. Okay? So to be consistent with them, we're going to use tau here as well. The transverse will be standing by, we'll use the tau subscript T and longitudinal tau subscript L. And tau going to be used for the general shear stress meaning. Let's move on. So let's see how it related. There. If we look at because we look at the area, if we look at the real element, it probably look like that. Okay? Notice, don't forget we donate point A here. that tau T, that transverse shear, cause zero moment. That longitudinal shear stress cause zero moment. We only care for that one and that one. Now, that is stress. To calculate moment, we need force. From the stress to force, we need area. That tau, that stress acting on the top here, and that stress acting at the side here. Okay, like that. So, if you're going to take moment, then this is what happening. Sigma moment at around point A is 0. Okay, that moment, let me be clear, this is moment about z-axis. Okay, z-axis in this picture. Now, the first term is that is the moment caused by that stress. That stress times the area, which is dx and dz. dx dz is the force. And then time the arm dy, it becomes a moment about point A, and of course it rotates anti-clockwise. The second term is that term caused by that stress. That stress working on a side way. Okay, so it becomes tau T times the area. The area is the height times the depth. The height is dy, the depth is dz. dy dz. And then the arm is dx. My apology, that one has to be dx. Okay, then it must be 0. I will change it in the sheet. And therefore, when we do this, it becomes equal, because that dx should be cancelled out with that, which is dx, and dy with dy, dz with, of course, dz. Okay, then the transverse shear stress and the longitudinal shear stress are equal. Therefore, we're going to use only the shear stress tau. Okay, the reason being, as I said, what we actually want to calculate is that one, but because we're going to link it to this axial stress caused by bending moment, which coming this way. Therefore, we need to actually calculate for TL for the longitudinal shear first, but they are equal to shear stress. Therefore, it means the same thing. Okay. So, since we established that the two components of the shear stress are equal, and therefore we just use the shear stress in general, tau. Now, let's look at the shear stress then. Okay, this picture here, well, they use downwards as minus W, meaning plus W is actually up. Okay, just to be consistent with the book. If we look at a one similar to when we do the bending moment, but this time we look at this one, then we look at the small element we just cut off with the dx. Of course, we have the bending moment and the shear on one side. When we move by dx, then the value of shear, the value of bending moment have changed. Therefore, it becomes the shear plus the change, and of course the bending moment plus the change. Now, because we are not going to take sigma Fy, this one here is actually just to simplify the picture. This, I emphasize, not a free body diagram. That one we can only use sigma Fx, because we haven't actually altered anything in the x direction. We cannot do sigma Fy because we ignore the shear. We cannot do the sigma moment because that shear also cause moment v dx. Okay, so only one equation left in this picture is sigma Fx equal to 0, which is apparently enough. Now, if we know the stress, well, let's assume that we can find the the area moment of the shear. Okay, there. Then we can find the pattern of the stress. Again, this bending moment is about z-axis. Okay, on the left hand side, Bm is one value. On the right hand side, Bm is another value. Therefore, two different equations signified by sigma and sigma prime. Now, if we move on, notice that now we don't have any shear stress happening. We don't even have shear force, But what we can do is we have to find where the shear stress will come from. Okay. Now the same picture, the same last picture, we just move it. Okay. Now to shear the shear stress again, we don't know how we're going to link the transverse shear stress. So what we look at, we're going to look at the longitudinal shear stress, but we can't see it. Why? Because we have no cut to see it. So we will supply with one more cut. There we are. Oh, this is the cross-section area. Let's assume at any shape. It just means any shape. And of course, we will talk about the axis of bending moment, the neutral axis, and the centroid as general, because well, we are looking at the bending moment stress as well. Now we're going to cut there at the solid line here. Okay, and of course when we cut it through the front view. This is the side view, cross-section area view. This is the front view. Okay, once we cut it, then if we draw either side there, okay, we cut this one here, we draw above the cut line. Once we cut it, then we see forces acting there. Of course, in this case, we see it in the form of stress. In this one here, tau, the shear stress. Of course, it is in fact the longitudinal shear stress, but they are the same. Transverse, longitudinal, the same value, only tau would do that. Okay? So now, if you see directional of the forces, of the stresses in fact, you should know that then in this case we only have forces that we look at, complete set of forces in the x direction. Okay, so we can combine them. Again, I repeat myself, at the beginning we said we cannot use sigma Fy, we cannot use sigma moment, but we still have sigma Fx valid, which we're going to use here. Now, how do we combine the force for that? Then we designate the small area. To be complete understanding the picture, then of course we need the bottom view. The bottom view is looking here because that is where the shear stress, the longitudinal shear stress is acting. Okay, so that area is needed to find total force of that sigma prime and that sigma. That bottom view is needed to find out the total force of tau. Okay, now on the stress pattern by the bending moment, like when we prove for anything else, if the stress is not consistent, it's not equally, it's not uniform, then we have to find a representative, in this case a small area. Now because the total area is called A, this cut area here, this cut area is called A prime, different area. And of course this small area here doesn't go down here, it only exists within A prime. Therefore, it is called the A prime there. The A prime. Okay? Now, we calculate the forces inside that small area. The force causing by sigma will be called dF in the small area, sorry. The force causing by sigma prime in that small area is called dF prime. And of course, it's just the stress times the area. Okay. Now that is only the force inside the area, the small force inside the area, the A prime. If we want total A prime, what do? Then we integrate total A prime. Notice this one stuck with prime because we don't integrate the total area. We only integrate inside the A prime. Okay. Notice one more thing though. The value I here is calculated before you cut A to see A prime. It is actually come when you talk about total area still. It will be calculated from A, not A prime. Okay? Of course, and that force, combination of force by the tau is just called tau, F tau, which is actually, because it's E or equal over this area, it's just tau times the height times the base, tau times t times the x. That one. Now we have the three force components. We just put it into equation of the of sigma fx equal to 0. And therefore we have that expression. That sigma, that term come from that expression going to the right hand side. That one come from there going to the right hand side, positive and positive. That one go to the left hand side, negative. Okay, so we started off this equation of sigma fx equal to 0. Because we run out of space, I'm going to move this equation upwards there and start proving from there. Okay, now we know the expression for sigma and sigma prime, then we can substitute into that expression. Okay, in the middle tau t dx, there is no need for change. This is normal substitution. Now this term here, notice that we can combine by plus. Therefore we can separate into two integration like that. Okay. Now notice that that is plus bm over I y prime dA. That one is minus bm over I y prime dA, the same. One is plus, one is minus, disappear. And then we have that expression left. Okay. Now once we got to that, then we move on and let's see that. Just move it upwards. Okay. Now, of course, we actually want to find tau here. Okay, so tau should be left on the left hand side, or we manipulate it first. Now, notice that the bending moment also, I is a constant. Of course, I belongs to the cross section. We haven't changed cross section yet. It's not about A prime though. I is about A, total A, right? We talked about it before. Now, I is constant, so we move out of the integration. Now, that dBm, how do I move it out? The word d means change, right? Right. However, you have to remember, bending moment change with x. This one we look at the consistent cross section. We are not moving around, just one cross section. Therefore, if you don't move x, bending moment doesn't change. The change in the bending moment between the 2 points remain exactly the same. That change is constant when you talk about area here. Okay, so meaning dBm for this integration is a constant and it can come out. Now that one there is when we find the centroid, equation to find the centroid, correct? Therefore, once we have that integration, geometrical, that one. What do I mean by that? And just to make it simpler, they designate that symbol y bar prime and A prime equal to capital Q. That Q is called the first moment of area. The area moment of inertia is the second moment, which we discussed already in the static. Okay. Here is what I mean. This is A prime, remember? We're talking about that integration. We have dA prime, that is dA prime. That is how we measure y bar prime. You integrate all over A prime, then you have the centroid position, meaning this one here represents that symbol and that one represents that symbol there. Notice that the measurement of y is from the same point or from the same line, that is from the neutral axis and 90 degrees to the neutral axis as well. So that is the definition for y bar prime and A prime. A prime must be cut, and that is the position where you actually look at the shear stress. Okay. Once we have that expression, substitute back into the main equation, we have that expression. And then we move, of course, t downwards, we move the x downwards. Now, if you differentiate bending moment with respect to x, what do you get? You get shear, and therefore we can find the shear stress from that equation. That is the formulation we used. Quite a long proof, isn't it? Well, let's go back a little bit. Okay. At first, we calculate, we prove that longitudinal shear stress exists. Meaning, when we usually talk about shear stress, we talk about this direction. Okay? Then we have longitudinal as well, the transverse and longitudinal. Now, we prove that they are, not only they exist, we also prove that longitudinal and transverse shear stress are equal. And then we use the bending moment to actually find out the longitudinal shear stress, which of course equal to transverse shear stress. Then because we actually prove this shear stress from the stress of bending moment, the value of I in the equation will be remain the same as the value of I used in bending moment, which means the total area, not the cut area, the total area. And all measurement must be from the neutral axis and 90 degrees to that neutral axis, the same neutral axis of the bending moment, of course. And that is the expression. Okay, Q, the expression for Q, and that summarizes what we have found today. Again, emphasize the name. Q is called the first moment of area. Next, I think we should see how this equation is used in our practical question. Okay, let's say we have a beam here. Okay, we have a cross section consistent. Okay, there are 2 points. This this cross section we show is actually at point 2 here. Okay, and on this cross section we show 2 points. One is called point B and one is called point D. What we want to find, practically I try to avoid the word point A because we are talking about area, right? Which is going to be too confusing. We also have centroid which use letter C, so that's why I call this point B and point D, to avoid those 2 letters. Okay. Then there's only one point load applied here, and what we want to know is what is the shear stress at point B and at point D. Okay. The 2 equations we use. Now that one is when we find our position, we want to know, we cut it. That is the kind of like the geometry property. We'll discuss about that later. Okay, and that will be the shear that we need, the I, the T, and the Q, of course. Okay, we go through it. T is where we cut. We will see it. Okay, firstly, let's find shear force at point 2. How do we find shear force? Well, we can find reactions and then cut and see again free body diagram. Then we find the shear force. Once we do that, then let's talk about I. This is the cross section area. I repeat myself here, and I will repeat myself again. The value of I is calculated from the total cross section area. No cut, no tip, nothing. Just the total one, right? In this case, this total area here, neutral axis is here. Again, there is no need to find this one because it's symmetry, up, down, and left, right. Okay, we know exactly where the centroid is. In this case, what I look at, this I look at the whole solid rectangle and 2 holes. Okay, and that's why I have this expression here. Okay, further detail, more details, then you should revise on statics. When we calculate I, we calculate V, we calculate I, we should have Q and T, right? There. Now let's talk about shear stress at point B first. Now, remember the proof. What we do, we cut that cross section at point B, parallel to neutral axis. There we are. That's how we cut it. Now, once we cut it, we look at the small area we just cut off. In this case, I will choose to look at the top area here, which means when I draw it, it will be just that. And that is what we call A prime. Notice we follow simply the step of proof. Once we cut it, that is area A prime. Do we know where centroid of this area A prime is? We do. Here. Oh, look at T first. T is the total width where we cut. In this case, is 14 centimeters because we cut here, right? Then the centroid. Do we know? Yes, of course. This is rectangle, half height, half base. Okay, and therefore we can calculate the Q for point B. We know T, then we substitute everything into the equation. There we are. Substitute it, calculators of course. Then we have the answer. What about point D? We repeat the step, okay? So now we want to know point D. What do we do first? We cut it first. Cut at where? Cut at point D. Cut how? Parallel to neutral axis. Then we draw the area. In this case, I will choose to draw the area down here. There we are. Okay. Now notice that this one here, the centroid is, well, the A prime is the area we cut off, right? Therefore, this one here, well, we have too small area. The T is actually where we cut. In this case, we cut at the width of 2 centimeters. T is of course 2 centimeters. Now to calculate Q, then we separate this into two small areas. Okay, that area and that area. There. Then we have C1 and of course C prime 1 and C prime 2. Okay. Then of course the normal calculation, and then we have that number. So again, we know shear we calculate already, we know I calculate already, then we have Q and T here, substitute into the equation. There we are. We have shear stress at point D. And as they say, it is as simple as that. Let's look at another example. Okay. Well, this is a beam, the cross section. Okay. Well, there is only one uniformly distributed load. What they want to know here is the maximum transverse shear stress in this beam, not specifically point. It's just the maximum it can have on this beam. Well, it is on this beam. If we look at our equation, notice that tau I is one value, consistent. In this T, in our case, is rectangle, so only one value as well. The two variable that affect the value of shear stress is in fact the shear force and the Q, the first moment of area. Okay, then tau will be max when V is max, shear force is max, and the first moment of area is max. How do we find maximum shear force? Of course, shear force diagram. Okay, just emphasize what I just said. Now, maximum shear stress, maximum shear force, actually, this one. Let's find out the reaction first, okay, as usual. There we are, sigma moment, sigma fx, sigma fy. Then we have the two. Once we have that, then of course we can draw the shear force diagram. When we draw the shear force diagram, then we pick up the maximum shear force value. Well, 112.5 or minus 127.5. Again, negative sign here is just direction. Negative doesn't mean always less than positive. It is just direction. So in this case, we must use absolute value, which means 127.5 is bigger than 112.5. And that will be the choice that we should use, maximum shear force. Now, once we do that, then we can move on. Now, the Q is max when the cut is at the neutral axis, because it's the biggest area A prime. And here we are. So if we cut on that part, we calculate the I first, the simple one. This is just BH cubed over 12 as usual. And then if we cut on the centroid, again parallel to the neutral axis, there we have that picture. Then of course that centroid we recalculate, because the centroid we used to find Q is not the centroid of that picture, not A, but must be from A prime. So we identify it again, but well, we can actually calculate. We know the T is also the width where we cut, in this case there, 10, right? Once we got everything, then we can calculate Q, Y, of course Y bar prime times A prime. And then next, we will just substitute everything into the known expression of tau. The tau max then can be calculated simply that way. And that is the answer. And if we summarize it, then it just asks for one question. Therefore, that is the one question. Okay, let's summarize what we have done for this lecture. The shear force. When we talk about formulation first. We talk about the longitudinal and transverse shear, that they are equal, and then we use the theory of the bending moment to prove the value of the shear stress, which means that a lot of shear stress calculation and measurement will belong to or will be associated with how we measure things in stress for the bending moment. Okay, and the area moment of inertia is also the same as the bending moment, and it must be calculated from total area, basically before the cut. And the measurement that we are talking about will come from the neutral, will be measured from and 90 degrees to the neutral axis. And of course, the neutral axis is the same one as belonging to the bending moment theory. And then we have the two expressions, the first moment of area, and then we have the equation for shear stress, and then of course we see the example. And that should conclude our lesson for today. Thank you very much.